Welcome to our lecture on clustering analysis. Today, we'll explore clustering, a fundamental technique in unsupervised machine learning. At its core, clustering is a method that helps us identify natural groupings in data, where similar objects are placed together while different objects are separated into different groups. Clustering algorithms generally fall into two main categories. Hierarchical clustering creates a tree-like structure of relationships, while non-hierarchical methods, like the k-means algorithm we'll focus on today, partition data into distinct groups. Let's dive into k-means clustering specifically. This algorithm partitions data into a user-specified number of clusters, which we call k. Each cluster is represented by its centroid, essentially the average position of all points in that cluster. The choice of k is crucial. Too few clusters might oversimplify your data structure, while too many could overcomplicate it. This balance is something we'll explore in more detail shortly. The k-means algorithm follows a straightforward iterative process. First, we choose our desired number of clusters, k. Then we initialize k centroids randomly in our data space. Next comes the core iteration. We assign each data point to its nearest centroid, then recalculate the centroids based on these new assignments. This process continues until cluster assignments stabilize. Let's watch this process in action. Here we have some scattered data points, and we'll use k-means to find 3 clusters. Notice how initially, our centroids are placed randomly. As we progress through each iteration, watch how points are assigned to their nearest centroid, indicated by taking on that centroid's color, and then how the centroids move to the center of their assigned points. In iteration 1, we see the initial assignments. In iteration 2, the centroids adjust their positions. By iteration 3, we've reached a stable configuration where further iterations wouldn't change our clustering. The effectiveness of k-means can be measured using a cost function. Mathematically, it's the sum of squared distances from each point to its assigned centroid. This formula shows how we calculate this cost, where j represents our total cost, summing over all clusters I and all points x in each cluster. The cost always decreases with each iteration, guaranteeing that our algorithm will eventually converge. When choosing the optimal number of clusters, we have several strategies available. Domain expertise is often the most reliable approach. If you know your data should naturally form a specific number of groups, that's valuable information. While we could optimize the sum of squared errors, this isn't recommended as it continually decreases with larger k values. This brings us to the elbow method, which provides a more balanced approach. The elbow method plots the cost function against different values of k. As we can see in this graph, the error decreases rapidly at first, but then begins to level off. This elbow in the curve, here at k equals 3, suggests an optimal number of clusters. After this point, adding more clusters yields diminishing returns. Think of it like bending an arm. The elbow point marks where the curve notably changes direction. Let's visualize what different k values mean in practice. In our first graph with k equals 2, we see underfitting, forcing 3 natural clusters into just 2 groups. This oversimplifies our data structure. With k equals 3, we achieve a good fit that matches the natural groupings in our data. But look what happens with k equals 4. We're artificially splitting 1 natural cluster into 2, a classic case of overfitting. Notice how the rightmost cluster gets divided, even though the points are naturally grouped together. K-means has several notable strengths that make it a popular choice. It's remarkably simple to implement, yet powerful in its applications. The algorithm is particularly efficient, with a time complexity of O(t)kn, where t is the number of iterations, k is the number of clusters, and n is the number of points. This efficiency, combined with its memory-friendly nature, makes it especially suitable for large data sets. However, we need to be aware of k-means limitations. The algorithm is sensitive to where we initially place our centroids. It struggles with clusters that aren't convex. Imagine trying to find a crescent-shaped cluster. The need to specify k in advance can be challenging when we don't know our data's structure, and the algorithm can be thrown off by noisy data and outliers. To conclude, let's summarize the key takeaways. K-means is a powerful tool when used appropriately. It works best with well-separated, roughly spherical clusters. Success heavily depends on choosing the right value for k. Use the elbow method as a guide, but defer to domain expertise when available. Always consider your data's characteristics before applying the algorithm, and remember to balance between underfitting and overfitting. Thank you for listening.